it's about 3 questions. The first question is here. So this one we finished last week. Question 1 finished. Now question 2, which is on accelerometer, has a seismic mass m. So here it's an accelerometer. The mass m, so this is mass m. Mass m of the accelerometer is given as 0.02 kilogram. Spring constant K is given as 2000 Newton per meter. Maximum displacement is given as plus or delta X. So please read the question. So given values are mass, spring constant K.
Doctor, the question is not appears.
The question is not appear. I will share it again. Let me try.
Yes, please.
Yeah, I will try again. Just. Is it okay now?
Yes.
Yeah, okay. An accelerometer has a seismic mass m. So mass m is given as 0.02 kilogram. Spring constant K equal to 2000 Newton per meter. Displacement delta X is plus or minus 1 centimeter. What is the maximum acceleration that can be measured? A, acceleration we have to calculate. What is the frequency, natural frequency omega n, or natural frequency omega n of the accelerometer? So we know that in an accelerometer, there is a mass connected with a spring to the vibrating table. As the body is attached with the table. As the body moves with an acceleration in this direction, then mass will move in opposite direction. So how much is the distance moved by the mass because of the vibration? Plus or minus 1 centimeter, because it's a vibration, hence it is plus 1 and minus 1. Spring constant K is given 2000. Mass is given, mass is 0.02 kilogram. We need to find the acceleration and frequency. We know that force is equal to K times delta X, spring principle. K is the spring index and delta X is the displacement, equal to mass times acceleration. Here acceleration is equal to K times delta X divided by mass. K is 2000 Newton per minute times delta X is 1 centimeter. 1 centimeter can be converted into meter, delta X, correct? Divided by m. M is the mass, mass is 0.02 kilogram. So using this equation, you can directly calculate acceleration. And acceleration is coming as, how much is the acceleration?
100?
Yeah, 102, right? So from here, directly we get acceleration. Okay. So it is, you can check how much it comes. Just calculate and give the value, please. It is 2 divided by 0.02, which is 100, correct? Meter per second square. So this is the maximum acceleration. Yeah, maximum acceleration. So we calculated maximum acceleration. Next is natural frequency. Natural frequency, you didn't study the equation. I will teach you now. 1 over 2 pi square root of K by M. In a vibrating table, natural frequency can be calculated as, this is natural frequency, 1 over 2 pi square root of K over M. 1 over 2 pi square root of K is the spring constant, which is given as 2000 Newton per meter, divided by M. M is the mass. So the mass is 0.02. So you get frequency, natural frequency as 50.33 hertz. So 50.33 hertz is the frequency, natural frequency of the system. So this equation is new to you. The natural frequency equal to 1 over, this is, you are going to study in vibrations also, square root of K by M. K is spring constant and M is mass. Any doubt in this? Any questions here?
No, doctor.
I can proceed, right? So this is very simple. Force is equal to K times delta X. This is based on spring. Based on springs. K delta X equal to mass times acceleration. From here we can calculate acceleration as K delta X over M. K given, delta X is plus or minus 1 divided by M equal to 100. Natural frequency is 1 over 2 pi square root of K by M. So from here we get the natural frequency. This is all about this question. Okay. Now we have next question given here. Please read the question before we start. Read the question. So it's an engine testing system. An engine is expected to develop 5 kilowatts. We don't know the engine, we produced it for 5 kilowatts. Now we have to check whether it is producing 5 kilowatts or how much torque it produces, that we have to find. So the output we expected is 5 kilowatt. We are not sure whether it is producing 5 kilowatt. We have to measure it. While running at an angular speed, the speed of the engine given. So here the power produced by the engine and the speed also given. So power produced by the engine. What is the power produced by the engine here? The power produced by the engine is 5 kilowatts. So this is the engine. So in this setup, what we do is a brake drum dynamometer. We call it as a brake drum dynamometer. The engine output is connected with the flywheel, and the flywheel is pressed, or the rotation of the flywheel is reduced or retarded by a brake. You can see here a block. This is the brake shoe. These are called brake shoe, and we apply load. We apply the load here. This is the loading screw. When we apply load here, when we tighten it, what will happen? The braking force to the flywheel will increase. The speed will decrease slowly, and finally the flywheel stop. At the point of stop, you can see that if you release it, what happens? It will come back to normal speed. If you press it and if it stops, the torque acting at that time will be equal to the torque produced by the flywheel. This is the basic mechanism of a torque arm dynamometer. So in a torque arm dynamometer, which is connected to the flywheel of an engine, it is rotating continuously. It is expected to produce 5 kilowatts, but we are not sure how much it produces. It is rotating at 1200 RPM. So we use a brake drum. We use a brake drum to find, we use a brake drum to apply the frictional force so that it stops. As it stops, the force, the torque produced will be equal to the frictional force produced will be equal to the torque produced by the engine. Now here, how much load you applied is 100 Newton. The load you apply here is 100 Newton. So because of this 100 Newton braking force, the flywheel stops. If you release 100 Newton, what happens? It comes back to normal torque. normal rotation. So the rotation is stopped by braking action by applying 100 Newton here. So this is the basic concept of a dynamometer, which is used to measure the torque acting in a system. Torque. The torque acting in a system is measured by the system called a dynamometer. So here in this dynamometer, we have a block rotating. This is the loading screw, and this is, as I explained before. Now, very simple principle is applied here. The simple principle means torque equal to force times distance. How much weight you apply here? Is it represented by F, or is it is represented by F? Yeah. This torque arm length you take it as L, and the force acting here, you are applying a force here, F. So that force times the distance L. This is the force and times length L. The force acting here is F times length will give you torque. This equation you studied before, torque equal to force times distance. So force is the weight. Force is what? Force is the weight you applied. L is the torque arm length. What is torque arm length? This is the torque arm length from center to the center of the weight. We call it as torque arm length in a dynamometer. So torque is equal to F times L. We know how much is F we have. F is 100 Newton. But unfortunately, we don't have L. We have to design. We have to tell us. We have to design, and we have to find what is the value of L to design this system. So ultimately, our aim is to find length of the arm to design this dynamometer. So it is proposed to design. That means find L dynamometer using a spring balance as a force measurement instrument. The spring balance can measure a maximum force of 100 Newton. Choose proper torque arm for the dynamometer. So L we have to find. We know that power equal to 2 pi nt by 60. So the power transmitted by the dynamometer is 5 times 10 to the power 3 equal to 2 pi times n. N is the speed. How much is the speed? 1200 RPM times T divided by 60. Okay. So from here, what is T? T equal to 60 times 5 times 10 to the power 3 divided by 2 pi times 1200. So here we have torque F times L. Here we have torque using power equation, another value. So torque both are equal. F times L equal to, this torque is F times L equal to 60. This is torque F times L. Force acting in the weight times L is torque. That torque is same as the torque calculated from the power 2 pi nt over 60. So here the value is 60 times 5 times 10 to the power 3 divided by 2 pi times 1200. I have F here. F is equal to 100. Can you substitute F 100 and find the length of the arm? Can you substitute F 100 and find length of the arm from here? So did you understand? We generated two equations for torque. One is by torque arm length and force, weight applied here. Weight is the force times L. Then from power equation 2 pi nd by 60, we have the equation for torque. So we generated two equations for torque, and when we equate them, FL equal to this, we get the value of L. Can you calculate how much is L?
0.39.
So L, the length of the arm is equal to 0.39, right? 0.39 meter, correct?
Yeah.
If it is
Yes.
meter, the length, okay. So the answer is I have three. The torque is 339 or the length.
Torque is 39.79.
Okay, okay. The force here is 100, right? Yeah, that is right. Your answer is right because they have taken F. I have taken F here as 90. That's the problem. It has to be 100, correct? If it is
Yep.
100, the final answer becomes 0.39. Yes, 3979 meter. Yes.
Why they put 100 multiply 0.9 equal
So
90?
that is just to they took the efficiency. I didn't specify any efficiency here, na? The spring balance efficiency. I assume that it has full efficiency because instead, if in the question if efficiency is not specified, I don't need to consider. That's why. They have considered in their design that it is 90% efficiency. If in the question I am giving you that take the efficiency of the system as 90%, then the force you have to multiply it by 90% and substitute here.
Okay.
Is that clear? If
Yes.
the efficiency is not given, you don't need to do that. You can directly substitute it as 100. Okay. Any system has got an efficiency. We don't know how much is the efficiency. It could be 1%, it could be 10%, it could be 20%, and it could be like 0% problem or losses or 100% efficient. Such systems are very rare, but still here they assumed the efficiency as 90 and calculated based on the assumed efficiency and got like this. But if I am not giving in the question, you don't need to use efficiency. You can directly use 100 and calculate it. Okay.
Okay.
Yeah, this is all about the questions, the two questions. I think we finished almost the questions there and maybe some repeating questions. So these are the things I finished. I will upload this today in SULMS, okay? In
Okay.
SULMS, where I am going to upload is these answers may be helpful for you. I will upload them in tutorial folder. I will upload them in tutorial folder. Let me see whether all. Yes. This is about. Okay. I have one more, it seems, right? This is ISQU quality control. The other one I already. Okay, this one I will upload it now. Otherwise, I will forget. Huh?
Okay, doctor.
Okay, so
Sir,
that's it.
these
Yeah,
questions are combined between module 3 and 4.
this is module 3 and 4. See, it starts from statistical quality control.
Okay.
Yeah, it's from module 3 and module 4. The other one I will also search. If I find it, I will upload that also in SULMS. Okay.
All right.
Yeah. Okay. Thank you very much for attending. Then we'll meet on Sunday. Not on Sunday, right? On Monday.
Yes.
Okay. Okay.
Okay, doctor. Thank you.
Thank you. Thank you. Thank you very much.